All right, welcome to the Explainer. Today, we're going to pull back the curtain on a tiny, really ingenious device that basically makes our entire high-tech world possible. It's a true unsung hero hiding inside everything from giant robotic arms to the printer on your desk. And it's all about answering one single fundamental question.
So let's just dive right in with this question. Think about all the precise machines around us. How does a robot, or a CNC machine, or even the elevator you rode this morning, how does it know not just how fast to go, but the exact direction it's moving, down to a practically microscopic level?
And the answer to that is so critical. We're talking about robotic surgery, where a single millimeter can make all the difference. Or think about those massive automated warehouses with thousands of robots zipping around complex paths. All of modern technology, it really depends on having perfect, repeatable control over position, speed, and especially direction. But here's the thing. Tracking this movement presents a really big challenge. A simple sensor, yeah, it might be able to count rotations to measure distance, but what happens if that rotation jitters back and forth? The sensor gets totally confused. It literally can't tell the difference between actual forward progress and just simple vibration. And that is the directional dilemma.
And this brings us right to that directional dilemma. It's this crucial limitation you find in more basic devices. You see, to solve this problem, engineers needed something way better than just a simple one-trick sensor.
And this slide just lays it out so clearly. A basic, single-channel encoder? Sure, it can count pulses, it can track speed or position. But look at that second row. It is completely blind to whether it's going forwards or backwards. Any little vibration could get counted as forward motion, and that leads to huge errors. It's a fatal flaw, really.
And that brings us to the really ingenious solution, the Quadrature Encoder. By adding just one more channel, it completely solves that directional dilemma with an elegant and, honestly, a surprisingly simple physical principle.
The entire secret is right here in this concept, in quadrature. Now, it sounds complicated, but all it really means is that the encoder produces two signals, channel A and channel B, that are intentionally offset from each other. So one signal is always about a quarter step ahead or a quarter step behind the other. That 90-degree offset, well, that's everything.
The device itself is just beautifully simple. At its heart, you've got this little spinning disc with these tiny, perfectly spaced slots cut into it. Then an LED shines light through those slots. And on the other side, there aren't one, but two photosensors. And the real key, the whole trick, is that those two sensors are positioned with a very slight physical offset. So as that disk rotates, each sensor sees this flickering pattern of light and dark, which generates a digital signal, basically a square wave of on and off pulses. But because the sensors are offset, the two pulse trains they create are also offset, and that produces that critical 90-degree phase shift we were just talking about.
Okay, so how does this 90-degree offset magically tell us the direction? Well, it all comes down to a really simple question. Which signal gets there first? And this just shows you the simple but really powerful logic behind it. When the disk spins clockwise, that first sensor, channel A, it sees the light first. The controller sees that A's signal went high before B's, and it knows, okay, add to the position count. But if the disk spins the other way, counterclockwise, then channel B leads channel A, and the controller knows to subtract. It's that simple. It's just asking, who's leading the dance? So the crucial point is this. By just watching which of the two signals is leading and which one is lagging, the system gets this perfect, rock-solid, unambiguous information about direction. No more getting confused by vibration, just pure, clean data on exactly which way things are moving.
But wait, there's more. This elegant two-channel design, it actually has another superpower. It doesn't just tell you the direction, it lets you quadruple the measurement resolution you can get from the physical disk. It dramatically increases precision.
And here's how it works. It's a process called X4 decoding. See, for every single slot that passes by the sensors, there are actually 4 distinct events that happen in order. Channel A goes up, then B goes up, then A goes down, then B goes down. A smart controller can count all 4 of those state changes. So a disk that has, say, 1,000 slots can actually give you 4,000 distinct position counts for every single revolution. That is a massive boost in precision.
So now that we kind of get how it works, let's look at the incredible impact this has on the world around us. This little sensor is truly the bedrock of modern automation.
In pretty much any factory, quadrature encoders are the backbone of the whole operation. They're what give robotic arms their precise, fluid motion. They guide the cutting heads of CNC machines with sub-millimeter accuracy. They keep these massive conveyor systems perfectly synchronized and make sure automated vehicles can navigate warehouse floors without a single mistake.
And you interact with this technology all the time, probably without even knowing it. An elevator uses one to level perfectly with your floor. Your office printer uses it to position the printhead with pinpoint accuracy. Even that satisfying kind of clicky control knob on a stereo or an appliance, yep, that's often a quadrature encoder, just counting your turns up and down. They're even in EVs, helping to optimize motor performance.
And they're absolutely critical for the really cutting-edge fields. The steady hand of a surgical robot? That is guided by quadrature encoders. A solar panel that needs to track the sun perfectly across the sky. Or a wind turbine that has to adjust its blades for maximum efficiency? Same technology. It's enabling a level of precision in fields we could have only dreamed up a few decades ago.
But, the story doesn't just stop there with a simple pulse counter. Just like, well, everything else in our world, the encoder itself is evolving. It's getting smarter.
And the leap forward is just so clear when you look at this comparison. We're moving away from a device that just spits out a stream of raw pulses to a truly smart device. These new encoders can communicate over digital networks, which means they can have a two-way conversation. They can monitor their own health, they can report faults, and they can even signal when they might need maintenance before they actually fail.
And why does that matter? Well, it matters immensely. Because this new, rich data is the absolute perfect fuel for artificial intelligence. AI models can analyze all the subtle variations in an encoder's signal to spot the early signs of mechanical wear, to predict failures, and even to optimize a machine's performance in real time for way better efficiency.
Which kind of leaves us with a final thought. For decades, the Quadrature Encoder has been this silent translator, turning physical movement into digital data that machines can understand. It gave them precision. But now, by feeding that same data into AI, we're not just telling machines where to go, we're actually teaching them to learn from their own movement. Encoder data really is the language of motion. And that just begs the question, what incredible new things will we build when AI becomes completely fluent?